Here's chapter 16, the PowerPoints. We'll go through these. This is just the first half, or part A. Alright, so one of the things it starts with is how our planet moves through space, and it's actually quite complicated if you include things like how the sun is moving through the galaxy. The sun is actually orbiting the center of our galaxy. How our galaxy, the Milky Way, is moving through space with respect to other galaxies, and so forth. So that we're gonna not really look at in this chapter. We're more interested in, the actual motions of the Earth with respect to the sun. So basically a solar, with respect to the solar system. Alright, so we'll start out here with the shape of the Earth. The Greeks thought the Earth was a perfect sphere, perfectly spherical, and it almost is, but it is not, actually. In fact, the distance between the center of the Earth and the equator is a little bit longer than the distance between the center of the Earth and the poles. Okay, so and that makes the Earth what we would call an oblate spheroid. So that's just a technical name for it. And it's actually not even that, not perfectly, but it's almost an oblate spheroid. So that's good enough. All right. So here are the motions of the Earth when we just think about the Earth with respect to the Sun, with respect to the rest of the solar system. And so obviously we have our yearly rotation around the Sun, and the yearly revolution. Actually, it's important to use these two words differently. Revolution is when an object orbits another object. Rotation is when the object spins around its own axis. So the rotation is the daily thing that we feel. We don't feel it, but that we sense from the sun rising in the east and setting in the west. Actually, let's talk about that briefly. The fact that the Earth is what's rotating. The fact that the sun rises in the east and sets in the west indicates that the Earth is spinning in the opposite direction. Okay, so if you looked out at the sun, from the northern hemisphere, and you watched it, obviously you don't look directly at the sun, but if you watched it as time went by, the sun would rotate in a clockwise direction. In fact, that from a sundial, that's where we get the sense of clockwise. The old analog clocks, as the dials spin around, they go in a clockwise direction. However, we actually are rotating. The Earth is rotating in the opposite direction, counterclockwise, and we're also revolving around the sun in a counterclockwise direction, as are all the planets. All the planets, sorry, I used the wrong word. They are undergoing revolution in a counterclockwise direction around the sun. So all the planets do that. However, there is this wobble that is talked about right here. That's also known as precession. It's actually a clockwise phenomena, and it's very, very slight. It's so slight that it takes this little wobble in the axis of the Earth. It's kind of like it comes from the effect of basically the Earth, in a really long time period, is slowing down its rotation, and it's actually the moon that's causing that. We'll get more into that a little bit later. But anyhow, this wobble is extremely slow. It takes, like I said, 26,000 years to complete one wobble, one complete oscillation of this wobble. So it's not anything any human would notice in their lifetime or in, in several generations. No one would actually notice it, but over really long geological time, you definitely notice it. All right, so these are the motions through space. Let's see. Whoops. And this. Let's skip this. All right. If you were to stand outside the solar system and just gaze at what's going on with the Earth. The Earth is obviously, it would take 1 year to go from this point all the way back to that same point, right? That's what we define a year, as the Earth orbits the Sun. The plane, by the way, that you notice, this thing, it's called the ecliptic. There is a plane that extends out into space from the center of the Sun, and all the planets line up in that plane. It's called the ecliptic. It's very, very important to know about in astronomy, because like I said, you find all the planets lined up along the ecliptic. But see, the thing about that is the Earth's orbit is the Earth's axis, I should say, is tilted with respect to the ecliptic. All right, more about that in a minute. Anyhow, if you were somehow observing the Earth over a great period of time, you would see the Earth going around the Sun, but also the Sun moving. So you'd have to be pretty far away from the solar system to actually see this. Probably have to have a pretty powerful telescope. And what the point is that the Earth is moving in a grand scheme in a helical fashion. So it's not just in undergoing revolutionary motion around the Sun, but the Sun is also moving at the same time. So that's just considering the Sun, the Sun and the Earth together. All right, so the revolution, of course, this is the thing that the Greeks had so much trouble accepting this. They thought that, of course, we were the center of the Earth, the center of the universe. And everything revolved about the Earth. So they didn't think that the Earth was moving around the Sun. Interestingly enough, of course, the Greeks knew that the Earth was round. That was perfectly acceptable. They could tell that several ways. One was, the fact that the further north you moved, the higher in the sky the North Star was. The North Star in the northern hemisphere, you can generally see the North Star pretty easily, and the other thing that they noticed is as you traveled further and further south, you would see new stars, new stars that you never saw before would come up over the horizon, and also they also noticed that when there was an eclipse, a lunar eclipse, you could see. They realized that was the Earth's, the moon passing through the Earth's shadow, and so they realized that the shadow was circular. All right, so the ecliptic is the actual path of the Sun through the sky. It's kind of looks like a sine wave. It goes as far as, like, if you were to map out the sky, it goes up and then comes down and then goes back up again. So that's we'll see a picture of it here hopefully in a minute or two. Our eclipse, the Earth travels around the Sun in what's called an elliptical orbit. This was actually discovered by a guy named Kepler about 400 years ago, and so the Earth is not going around, the Sun in a perfectly circular orbit. It gets a little closer to the Sun, and that actually happens in January by about as it says here, 2.5 million kilometers, about roughly 1.5 million miles, and it gets a little further from the sun, and that happens in the month of July, right in early July. And so what that means, as far as sunlight goes, we receive a little bit more solar energy in the month of January, and that might seem confusing, especially to people who live in the northern hemisphere, because obviously January is is a winter month. The thing is that the seasons are not really controlled by this getting closer or getting further from the sun. What really does that, of course, is the tilt of the Earth. The axis of the Earth is tilted with respect to the ecliptic. All right, and actually we see that here. Okay, so this is here we have the Earth tilted 23.5 degrees. The thing is, that tilt, except for the slight wobble that I talked about earlier, the precession, as it's called, precession, which basically can be ignored throughout, and in several human lifetimes. You're never ever going to notice precession, so it's not like a daily thing that you'd ever see. So basically what happens is the north and south poles of the Earth, this imaginary line that extends from the North Pole and extends from the South Pole into space, that never ever changes the orientation. So as the Earth goes around the sun, that the North Pole, right now, for example, it's pointing at the North Star, at what we call the North Star, and that never changes the orientation. So we have, during a one-year cycle, you have the northern hemisphere tilted, in this example over here, away from the sun. Then and so that would be the first day of winter, and then in March, and these always happen right around the 22nd. They don't exactly happen always on the 22nd. Sometimes it's the 21st. Sometimes it's as late as the 23rd or even the 20th. That's because the length of the year is not exactly 365 days. Anyhow, so here is March, and also notice 6 months later, this is September. During those times, those are called the equinoxes, by the way, as it says down here. During the equinoxes, there's equal amounts of daytime and nighttime. This is called a solstice. For the northern hemisphere, this would be the winter solstice. Notice the opposite is happening for the southern hemisphere. This is the first day, December 21st is the first day of summer for the southern hemisphere. All right, so we go 6 months later, and now the northern hemisphere is pointing towards the sun. It happens right around June 21st. And that, of course, is the first day of summer for the northern hemisphere, and conversely, the first day of winter for the southern hemisphere. All right, and there is here's the ecliptic, and we have this tilt, and so that's what's reflected in the figure that I just showed you. How that this is the cause of the seasons. Because of this tilt, and so you're having the northern and southern hemisphere either pointing towards or away from the sun, and so you're getting different amounts of sunlight as the year goes on. All right, let's stop there, and we'll continue on in the next video.